Hey everyone, and welcome back to another one of my deep learning tutorials. In this video, we'll take a look at the parameters that define our neural networks. We'll discuss activation functions, learning rates, as well as the weights and biases. We'll also talk about what a learnable parameter is, as well as classify which of these parameters are learnable. But before we jump into it, I'd like us to recap on the structure of the neural network. If you watched my Intro to Artificial Neural Networks video, you're probably familiar with this image and structure. But if you're not familiar with that video, you might want to check it out. The main takeaway from the video is that the basic structure of our neural network consists of these neurons or nodes grouped into layers. The layers include the input layer, which is where our neural net will receive the data it will process, and the output layer, which is where our neural network displays predictions. We also have hidden layers in between to help with the network's computations. Alright, now that we've recapped on the structure of the artificial neural network, I'll jump into the main focus of this video, which is the parameters of the neural network. The first parameter we'll discuss are the weights. The weights represent the strength of the connection between two neurons. A weight decides how much the value of one neuron influences the value of the succeeding neuron. If the magnitude of the weight in a connection between neuron A and neuron B is close to 0, then neuron A will have little or no influence on neuron B. But a weight with a larger magnitude will mean that neuron A has a greater influence on neuron B, while negative weights will mean increasing the input will decrease the value of the output. In a neural network, each connection between neurons has an assigned weight, and the strongest connections will have the largest weights. In this example, the weights in the connection between neuron A and X is greater than the one between neuron B and X, so neuron A will have more influence on the value of neuron X. Initially, the model may begin with randomly assigned weights, but when we train our network, we modify the weights until the model's predictions are more accurate. So the weights are a learnable parameter. A learnable parameter is a neural network parameter that can be modified during training. Now that we understand what the weights are, we'll move on to the bias of a neuron. Simply put, the bias is a constant value that will be added to the product of the inputs and weight. Its purpose is to offset the results and also increase the flexibility of our network a bit. The bias of a neuron gets modified during training, so this too is a learnable parameter. Let's think of a network that only has two neurons, the input neuron A and the output neuron B. This type of a model is a linear regression model. Without a bias, the value of the output neuron will be the product of the input neuron and the weight W. This is how the graph for our model would behave as we modify the weights. While the slope for our model may change, it is still inflexible as the graph is fixed at one point. Adding a bias to neuron B will add some flexibility to our model, and the output for our model will no longer depend on just the product between the value of neuron A and the weight. We'll add a constant to this value, and the constant will be our bias. The result for this is a more flexible model. The graph for our model is no longer centered at one point, but it can change intercepts as we modify the bias. After we multiply the inputs to our neuron with the weights and add our bias, the result is sent through an activation function to determine whether the neuron is active or not. Activation functions are mathematical functions attached to a neuron in a neural network. These functions help us normalize the input of each neuron to a range between 0 and 1, or a range between -1 and 1. In simpler terms, they help us determine whether a neuron is active or not. The activation function of a neuron will not be modified during training, so the activation functions are non-learnable parameters of a neural network. There are a number of mathematical functions that could be used as activation functions for our neurons, and depending on the use case for your model, you may have to choose from some of these functions. One of the simplest activation functions is a binary step function. This activation function is based on a threshold. The neuron will only be activated if the input is above the threshold. While this function is simple to understand, it is not necessarily the best to use. One of its limitations is that the output for the binary step function can only be one of two constants, 0 or 1. This means that this function is non-differentiable. Currently, one of the best ways to train neural networks with multiple layers is through gradient descent and backpropagation. These will be discussed in depth in a later video, but basically they involve taking the derivative of the activation function to proportionately modify the weights and biases of the network. Since the binary step function is non-differentiable, gradient descent won't make any progress modifying the weights and biases. We could also use linear functions as our activation functions. These functions take the input of the neuron and produce an output signal proportional to the input. Unlike binary step functions, linear functions do not only activate the neuron, but they output the degree of activation to the neuron that is proportional to the neuron's input. While linear functions are a bit of an improvement from the binary step function, gradient descent with backpropagation would still not work with these functions, even though linear functions are differentiable. The derivative of the slope of these functions is a constant, and it has no relation to the input the function gets, which means we have constant gradient descent occurring. So it is not possible for backpropagation to know which weights to modify to get a better prediction. Also, with linear activation functions, nesting hidden layers with the same function would have no effect on the performance of our model. The hidden layers would basically behave like one layer. For backpropagation and gradient descent to be effective, we need nonlinear activation functions. There are a number of nonlinear activation functions to pick from when building your neural network. The first nonlinear activation we have is the sigmoid function. The output values for sigmoid are bound between 0 and 1. Sigmoid has a smooth gradient, and it normalizes the output of each neuron. This prevents the drastic change in the output values due to minor changes in the input. An alternative to sigmoid is the hyperbolic tangent, or TanH function. This function is similar to sigmoid in every way except for minor differences. While sigmoid outputs are bound between 0 and 1, the outputs for the hyperbolic tangent are bound between -1 and 1. This function is also zero-centered, and these changes allow the hyperbolic tangent to have strong negative, neutral, and positive outputs. Another popular activation function is the rectified linear unit function, or ReLU for short. ReLU is a piecewise function that outputs the input directly if our input is positive, and outputs 0 for any negative input. Since ReLU is a simple function that does not perform any complex exponential operations, it is more computationally efficient than sigmoid and the hyperbolic tangent. Many neural networks use ReLU, and the reason for its popularity is that, compared to most activation functions, ReLU helps the model converge to a solution more quickly. Hopefully that gives you a clear understanding of activation functions, and we'll now move on to the final point of this video, which is the learning rate of a neural network, which some people refer to as the step size. The learning rate is a parameter of the neural network that controls how quickly our model will converge to a solution, or learn from the data we feed into it. This parameter often has a value between 0 and 1. Giving a model a small learning rate may require you to pass data several times to the model before it converges to a solution, and with a larger learning rate, the model may converge more quickly. However, a learning rate that is too large may not give us the best solution, and our model may diverge from the solution. The learning rate is not a learnable parameter of the neural network, and it is only configured when the network is declared. We'll discuss the learning rate in greater depth when we talk about the training of a neural network, but hopefully this gives you a glimpse of what it actually does. That will be all for this video. Be sure to leave a like if you enjoyed it, and thank you guys for watching.